problem. So you see here 3 consistent answers of 5 hours. One person solved it algebraically, and they have 2 separate things being added together on this side to equal 760. The second person solved it algebraically. They have something that's worth the same on the left side. They just wrote it as 1 quantity instead of 2. The third person said 152 equals 1 hour, and that they noticed that if you times that by 5, you got 760, so that would be in 5 hours. So they just did it kind of numerically without any algebra involved. Did anybody else have another way that they would think about this problem too? Matt? Okay. So you have like Mr. Williams, right? And he's going one way. And then you have Miss Tran, and she's going the other way. And he's going at 80 miles per hour. And she's going at 72. Thanks. Okay. And so then you would just kind of see how many hours and then if it met that criteria. Okay, perfect. So value in all of these things. So this is kind of a picture take on what was happening right here with the 152 equals 1 hour and then seeing that times 5 would get it to be a certain distance apart. Both of those things have value in understanding that you added up the 80 and the 72 to equal that 152 miles apart, okay, and to understand that. The problem with this problem is, what if I had then asked, in how many hours will they be 805 miles apart? 760 was nice, right? True? Okay. So this still gives you a good idea of what's going on. And numerically, you'd get a good idea of what's going on. But if 152 times 5 didn't work out so nicely to be 760, you'd then have to start like adjusting between numbers, putting decimals in there, and guessing and checking yourself, right? So that's where the algebra can come into play. So this is what I want you guys to realize. I am not dictating that you do these problems algebraically. If you can solve them in whatever method you solved them before, awesome. But if somebody changed the number in this problem from 760 to 805 and now you can't solve it, you need another method, right? Another way to solve it. So the algebraic methods up here, they could solve it whether x came out to be a whole number or not, right? At this point, if I solved for x and I got, I don't know, some big giant decimal or some fraction, it would be fine. I would just have the fraction and I'd be done. But that could have been a lot harder for me to find numerically or just by drawing the pictures and counting it. Does that make sense to everybody? So these are all good methods. Don't let anybody take any mathematical sense you have away from you. Just get new ideas to add to different ways you could do this problem if it didn't work out so nicely, okay? So I want to talk about where they got these algebraic equations from, which are essentially the same, starting with a little bit of structure. Again, you don't have to do it this way. If you know how they got this equation, fine, okay? Then you can build that equation and just go. But for those of us that are like, I have no idea, then we need a new starting place to be able to look at it, okay? So since this problem is about how far people traveled, how fast they traveled, and how much time it took, the distance rate time equation is helpful, okay? But there's 2 of these going on because there's 2 people traveling in different directions at different speeds. So one of these equations is helpful for Mr. Williams' situation, and one is helpful for Ms. Tran's situation, and then we have to see what they look like together. So for Mr. Williams, okay, his distance that he traveled is going to be his rate, which was 80 miles per hour, times however long he traveled, okay? Ms. Tran's distance is going to be 72, because that was her rate, times however much time she traveled. Now, notice what I've done here. With this D, I put a little W next to it because I'm letting that represent Mr. Williams' distance, right? And with this D, I put a little T next to it because for me, that's helping me remember that this D represents Ms. Tran's distance. And are these D's necessarily the same? Has each person traveled the same distance? Probably not, since their rates are not the same, right? But notice that with the T's, I just let them both be T. Why didn't I have to say, like, oh, this is the time that Mr. Williams has been gone, and this is the time that Ms. Tran has been gone? How come I didn't need different t's? Okay, so time doesn't change. It can actually change, but why doesn't it change in this problem? Good. They left the house at the same time, right? So they have both been gone the same amount of time. Have they both traveled the same distance? No, because they're traveling at different rates, okay? Then it is, what do we do with these things? So we haven't used the 760 yet, and it says in how many hours. So we want an equation that t is what we're solving for, right? In how many hours will they be 760 miles apart? This is where the picture is really nice. If you wanted to see how far apart they are right now, okay, what do you do with how far Miss Tran's gone and how far Mr. Williams has gone to get how far apart they are? You add them together. So in this problem, how far apart they are, and again, a lot of you guys know this without all this work. I'm not asking you to do all this work. I'm trying to give people that aren't sure what to do a foundation that they could start on. So in this problem, how far apart they are is going to be dictated by adding up the two distances that they've traveled because they're going in different directions. So how far is going to be his distance plus her distance, okay? And what is that supposed to add up to be for us to solve this problem? 760, because we want them to be 760 miles apart, right? So we want 760 to equal, and it has to equal his distance plus her distance. But having those two things in there together doesn't help me at all because these are two different things, right? But according to my little equation over here, his distance can be represented as 80 times the amount of time, and her distance can be represented as 72 times the amount of time. And now you can see why it was okay for these people just to say 80 times x plus 72x equals 760. Or to understand that each hour, they're going to be 152 miles apart and just say 152x equals 760. Okay? So basically, I'm just substituting the values that I came up with in here. So 80t plus 72t. And then I can go ahead and solve for t, which you saw that those people already did algebraically, but they just used x. So we get that t is 5, okay? And then when we look back at the problem, the rate was given in miles per hour, so our time here is representing hours. So we have 5 hours. Again, I am not saying this is the easiest way to do the problem. I am not saying that your way is not as good as this. What I am saying is that if you just do it numerically, you have to have a backup plan for when it doesn't go in evenly. Okay? And if you don't already understand some sort of algebraic setup, then try and grasp what's going on in the problem. Here's a very structured way of doing it. I'm not saying it's the right way. I'm saying it's a very structured way. Okay? That you can pull together distant rate time equations for each scenario. You can look at what's relating them in the problem and then try to put together a solvable equation. Okay? Any questions about that? So we could draw pictures, okay? We can use number sense. We can use algebra equations we already know, or we can lean on the distance rate time equation to help us. A lot of different ways to solve them, okay? All right, next problem up. Okay, at 8 a.m., Stephen leaves home on a business trip driving 35 miles per hour. A half hour later, Angie discovers that he forgot his briefcase. She drives 50 miles per hour to catch up with him. If she is delayed 15 minutes with a flat tire, when will she catch up with Stephen? Okay? All right. So, your turn again. In your group, take some time. Okay? Figure out a method that will work. I'm not taking away any method that you guys have done, but let's look at what's going on. So first, I do like starting with a picture so I at least understand what's happening. It helps me sometimes with when I'm supposed to add or subtract. Okay, here's our little house, okay? I don't really draw real pictures. I draw math pictures. Okay, so Stephen leaves home on a business trip. There goes Stephen, okay, driving his 35 miles per hour. Then Angie goes after him, driving 50 miles per hour, okay? She has all this flat tire action and stuff going on. And then the question is, when will she catch up with him? Okay? So what are we trying to figure out in this problem? A time, okay? Something about a time, and when she'll catch up with him. when does this problem end? The scenario's done when what happens? When she catches up to him, which means what about distance, rate, and time? Equal distances, right? Because they've both left the house and gone the same amount, okay? So let's talk about what their distances look like so we can then set them equal to each other, okay? So the distance for Steve, he's traveling a rate of 35 miles per hour times some amount of time that he's been out of the house. Fair enough? Okay. Then Angie's distance is 50 miles per hour times the time that she has been out of the house, but it is different than his time because they didn't leave at the same time, right? So I have two options. I either have to put a new time variable here, which is super annoying, okay? Or I can use still t if I adjust t for how much time needs to be adjusted for the amount of time she's left the house, okay? Monet or Jenny, either one of you guys, duke it out. Okay, so it is t minus something because she's been out of the house less time than him, and it is a 45-minute period of time, but we have to be very careful about our expression of that. Good. We're going to use 3/4 because what does t represent in this problem? An hour. So the problem with doing t minus 45 is you're really saying she left 45 hours after he did. Okay? And the reason we know t is hours is because all the rates are given to us in miles per hour. So if t is going to represent an amount of hours, then we need to convert that 45 minutes to be representative of hours, which is 3/4 or 0.75, however you like to do that. Okay? So knowing these things helps me write the equation. And then the question I asked you guys earlier was to know what to do with the equations. We said the problem is done when she catches up with him, which means their distances are the same. Last time is when their distances added up to 760, right? So we took their two distances, added them together, and made them equal to 760. This problem ends when their distances are the same, when they've caught up to each other. So what I want to do is set his distance equal to her distance, okay? So I'm going to write this step out, which some of you probably are like, Miss Dahl, I don't need to write that. That's fine, okay? The problem ends when Stephen's distance and Angie's distance are the same, so she's caught up with him, which means when his 35t, that represents the distance he's traveled, is the same as her 50 times t minus 0.75. Okay? So then we can do some computing. What is 0.75 times 50? Thanks, people. I knew I could depend on you. All right, and then if I subtract 50 from each side, negative 15t equals negative 37.5. So t is equal to what? 2.5? Okay, yeah, that makes sense. All right, so t is equal to 2.5. This does mean 2.5 hours, and t was kind of the base time starting at what? Starting when Stephen left the house or starting when Angie left the house? Stephen, because he was just with t, right? If we wanted to calculate when Angie left the house or how much time she's been gone, we would have to take this and subtract this from it to see how much time she's been gone from the house, right? Because this is her amount of time on the road, okay? Yes? Okay. Did you guys convert anything else in the problem? Right. Okay, so they did t minus 45 and they got 150, but then they had to convert it back to hours. So you had to do that extra step at the end, which is fine, okay? But I just don't want people writing. They had enough sense to go, I heard them over go, 150 hours. That doesn't make sense, so that's good.
So when you plug in t back into A, are you adding the 2.5 hours onto the 8 a.m. or do you still have to add something?
Yeah, no, onto the 8 a.m. So, again, how long has each person been gone from the house? If t is 2.5 hours, t by itself was in Stephen's equation. He's been gone on the road for 2.5 hours. In Angie's equation, we have t minus the 3/4 of an hour that before that. So if you wanted to find out how much time Angie's been gone, you would take the 2.5 hours, but you'd subtract 0.75. Okay? So we're just going to add the 2.5 hours onto his 8 o'clock start time, right? So he left at 8 o'clock. 2.5 hours later, she caught up to him, so it would be at 10:30 a.m. Is this okay? All right, so again, we're not taking away any of the ways that we've learned before. We're just adding another structure if we feel stuck with the methods we knew from before and they're just not working. Okay? All right, you guys ready for another one? That wasn't very enthusiastic. There was nothing. All right, good job, good job. Okay, so we have 7 answers. Yeah. Maybe these ones are the same. I don't know. That's point. Oh no, 0.75 would be 45. No, yeah, they're all different. Yeah. Okay. So 6 of them are wrong. Maybe one of them's right. Maybe 7 of them are wrong. I don't know. We'll see. All right. So to understand this, what we really want is this. We don't really want how many hours it took them to do the car. What we really want is their rate, right? How much of the car they can get done per hour. Because if I said, Matt can do 1/3 of a car per hour, and I can do 1/2 of a car per hour, then I would say, okay, together, like if Matt can do 1/3 and I can do 1/2, and we add those up, 3, 6, 2, we get like 5/6 of the car in an hour. But at least then we're working with like same terms, right? It's how much of the car I can get done in 1 hour, and how much he can get done in 1 hour. That makes more sense to then add together and say, together we can do this much of the car per hour. So the trick here is getting each person's rate, because then we can add the rates together. So to understand that, if you're having a hard time, we can still use distance, rate, time. It's just that distance isn't really what we're measuring anymore. We're more measuring like how many jobs get done, okay? So it says Olivia, so like for Olivia, it says she can do 1 wash and wax. Oh, that's nice. Okay, I don't know what's going on with either my projector or my alignment is really messed up, so sorry. Okay, she can do 1 wash and wax. Okay, we don't know her rate. Okay, what we know is her time. We know she can do 1 wash and wax. Okay, and she does that in 3 hours. Okay, this information tells me that Olivia's rate then is 1/3. She gets 1/3 of the car done in an hour. Does that make sense? Okay. I know that you can read that and be like, yeah, Ms. Dahl, I knew her rate was 1/3 when I read it. I don't need to write the little distance, rate, time equation. That's great. Okay, but if they don't tell you 1 car in this many hours, it might be harder to figure out the rate. Okay, so then there's George. He does 1 wash and wax, and it takes him 4 hours, which means George's rate is 1/4. So this is the rate for Olivia. This is the rate for George. Okay? Now this information is a little more useful because I know that in like an hour period of time, Olivia can get 1/3 of a car done and George can get 1/4 of a car done. So now when I hear they're working together, I can just add stuff together now that I've written it as a rate. Okay? So their rate together is going to be Olivia rate plus George's rate. So she's getting 1/3 of it done per hour. Yeah, I'm having some issues, sorry. He's getting 1/4 of it done per hour. If you add this up, I don't know, this is like 4/12, like 3/12, thank you. This is 7/12. So now I know at least that working together, they work at a rate of 7/12 of a car per hour, right? Now I can go answer the question. So all of this was analyzing the information given to actually get a together rate, so I can go do a together calculation now that they're working together. Okay? Now that they're working together, I can answer their question. If Olivia and George work together, how long will it take them to wash and wax 1 car? So now I'm looking at all of this stuff from the viewpoint of togetherness. Okay? Together. Yeah, Cody. Well, let's see, watch and see how we finish, and then I'll come back to your question. Okay, So together, let us finish and then I'll answer that question. Together, okay, you guys might not need it, but some people in this room do. I've watched. I know how the test results look. So if you don't need it, that's fine. You have a way of doing it, but other people need it. So together, what's happening, for them to get one job done, okay, distance has now become number of jobs to get done, and they're working at a rate of 7/12, how much time is that going to take them? How do I solve this equation? No, I just have to get t alone. Good. I'm just going to multiply by the reciprocal of that rate. Okay. So Cody, to come back to your question, this was the rate of how much car they get done per hour. Okay. So to get one full car done, you have to multiply 7/12 times some amount of hours. Okay. So to solve that, it's going to look like 12 over 7 equals our time. Okay. And 12 divided by 7 is 1.71. Now, in hours and minutes, if you want a better understanding of it, this is 1 hour, and then it's 0.71 of an hour, and we can multiply that 0.71 times 60 to figure out how many minutes that is. So what's 0.71 times 60? Okay? I'm not saying that you have to do it this way again, but I'm trying to give you guys perspective that what you're trying to do mathematically, how you just want to like add it together or average what's going on, only works if you have a really specific type of information. You can't just add together how many hours it takes them or average them. You really need to get their like rate of work per hour in order to combine it with someone else's rate of work per hour to increase the amount of work per hour getting done. Okay? Is this all right with everybody? Now, I know there are little charts and stuff that you guys have done these in other classes, kind of like the mixture problems. If that works for you, do it that way. I have no problem with that. Okay? I'm just showing you guys a different way. Yeah, Eric. Uh-huh. Okay, what did you do? I'm going to show you guys the distance, rate, time way. Again, it's just a way. It's not the way. Okay? So we think about the trip upstream and the trip downstream. So like in all the other problems, you know how it was like train A or train B, you have person A or person B, those kinds of things. They all have their own distance, rate, time, and then to solve the equation, we try to figure out how those two things are related. Do we need to add them to a certain amount? Do we need to set them equal? Different things like that. So it says a 9-mile trip downstream, okay? So it tells us the distance, right? So for the downstream, it says a 9-mile trip downstream took the same amount of time as a 3-mile trip upstream. So I know the distances for each of them, right? The rate. I know how fast the boat goes. How fast does the boat go? 3 miles per hour. And each time it is traveling at a rate of 3 miles per hour. But there's something else happening. Okay, the current. When you're going downstream, the current is helping you, okay, and is making you go that much faster. When you have to work against the current, think about it. If the current's 3 miles per hour and you're 3 miles per hour and you're trying to go against it, where are you going to go? Nowhere. So when you're going upstream, it's your strength or your miles per hour versus the current, so it's being subtracted from it, okay? And then it said these trips took the same amount of time, so I can use this same letter T. Alex? We aren't given any information about wind, but the airplane problems with wind would be the same as the current problems here. So if this was an airplane problem, it is about the headwind or tailwind, I'd be like plus W and minus W to the airplane speed, okay? Now, to solve this, we want to know, okay, it says the time took the same amount of time. So I basically have a system here, but if you distribute the T, it's going to get ugly because there's going to be T in multiple places. My advice, since we want to know what the current is to rewrite each of these in terms of t. In other words, solve for, in terms of c. So solve for t. And then use something similar to a substitution method. If you want the time to be equal, which the problem says it is, then this should equal this, and that's an equation I can solve and get the value of the current. So then I could set 3 over 3 minus c equal to 9 over 3 plus c. I can cross multiply, and I can solve for the value of the current, so I can know the current speed. Okay? And that will be in miles per hour, because that's what our other given measurements were. Does that make sense? All right, I'm going to stop there.